Hello, my friends. Call us Stephanie Meyer's Twilight Breaking Dawn the way we're back at it again, this time for round 4 of our flipped classroom. While there are no baby human vampire hybrids waiting for us in our 4th unit of the year, things are definitely going to get a little more interesting from here on out. Because for the past 4 units, we've almost exclusively spent our time solving equations and inequalities with a single type of variable. In math, we would say that means they were in one variable. But in math, as we've seen time and again, the name of the game for us is often in our ability to iterate. In other words, taking our foundations and seeing how far we can push them to solve more and more complex problems. All of that to say, solving equations with one variable is no longer good enough for us anymore. We want to be able to identify solutions for those in multiple variables too. So for our first class of Unit 4, let's get started with talking about solving some equations in 2 variables and also refreshing us on some of the basics of graphing. Now, if it's any consolation, our focus, at least for now, is still going to be on solving linear equations. Remind me, by definition, what makes an equation or an expression or an inequality linear? Go. 5, 4, 3, 2, 76. Well, a linear equation, by definition, we said that attached to all of the variables is an exponent of 1. So by definition, we say that a linear equation is an equation where all of the variables, even if there is more than one of them, have an exponent of 1. So no x squareds, no y cubes, all just x's and y's. I've given something away here, but for equations and even inequalities in 2 variables, by convention, usually the 2 variables that mathematicians use are x and y. So more often than not, these are the 2 variables that you're going to see. For example, take something like x minus y equals 7. If I want to solve this, remember, what does it mean to solve? What am I trying to do and how do I do it? 5, 4, 3, 2, 77. Oh, you've made me so happy you shouted it out. To solve an equation, of course, means to make it true. And I make it true by finding solutions, right? I'm trying to find things that when I plug in for the variables, I get a true statement. So by definition, right, when I'm trying to solve an equation or an inequality, what I'm trying to do is find a value or values of our variable or variables that make or makes, depending on our conjugation, the equation, or technically the inequality, but we'll just leave it to equation here, true. Can you find some solutions to x minus y equals 7? What are some pairs of numbers for x and y that you could identify that would make this equation true? Go. All right, hopefully you've played around. Let me give you a couple of my own. So like, for example, something maybe kind of obvious or at least small, if I had like x equals 8 and y equals 1. Well here, if I wanted to check if this was a solution, what would I do? 5, 4, 3, 2, 78. Well, if I wanted to check if this was a solution, all I would need to do is substitute. So I'm going to take 8 minus 1. Is 8 minus 1 equal to 7? Well, yes, this is absolutely a solution. I could get wonky with it. I could throw some negatives in there. What if I had like x equals negative 14 and y equals negative 21? Well, to check my work, again, all I need to do is substitute. So is negative 14 minus negative 21 equal to 7? Well, negative 14 minus 21 means negative 14 plus 21. Is negative 14 plus 21 equal to 7? Well, yes, this is absolutely a solution. And then I could get even really weirder with this, right? What if I took x equals 1,000 and 7 and y equals 1,000? Well, all I would need to do is substitute. Is 1,007 minus 1,000 equal to 7? Well, yes, this is absolutely a solution too. So I could find potentially infinitely many solutions to these equations. But what do you notice about all of them? Well, unlike the equations that we were finding solutions to before, usually we were only interested in things that had one part, right? It was just x equals 5. But now when I find a value of x that works, I also need attached to it a value of y. So the thing that we'll observe here is that now, instead of only having a single part, our solutions are going to be, and you heard me use this word before, pairs of numbers. They are attached to each other. I can't get away with just one. We represent these solutions as what we call ordered pairs. And by convention, the way that we have chosen to order them is in the following form. So the general form of an ordered pair starts with a parentheses, and then usually if I'm talking about values of x and y, we put the x value first, followed by the y value, separated by a comma, and ended with a parentheses. By the way, notice, what does this notation look a lot like? Is there a notation in a previous unit that this resembles a lot? 5, 4, 3, 2, 79. Well, this one looks a lot like our interval notation. Specifically, right, if I was working with an interval for maybe like a sandwich or some part of a number line, maybe there was an infinity or a negative infinity in there. The important thing about this is the context. In this context of solving equations, this is talking about a solution. In the context of graphing an inequality, for example, this was talking about a range on a number line. So the context here is going to be important for determining what our notation in that context is representing. Real quick, can you write each of the solutions above that we identified as ordered pairs? Go. Alrighty, let's do it. Well, by convention, the x number goes first, followed by the y number. So I take the 8 and then write the 1 after, separated by a comma with parentheses around. Here I had x was negative 14, so negative 14 will come first, followed by the y, which is negative 21, end in parentheses. And then finally I had parentheses, 1,007 for our x value, followed by 1,000 for our y value. By the way, I'm calling them ordered. What order do you think they're in? Very nice, invisible person. Well, if the x is coming before the y, very likely that they are in alphabetical order. So if I were to encounter something with a's and b's in the equations, I'd probably put a and b, or a before b. If I had some equation with m's and n's, I'd probably put the m before n in ordered pair notation. For now, though, we're going to get familiar just using x's and y's. So one reason why I call them ordered is because they're alphabetical. What other reasons do you think I might have for calling them ordered? Well, let's take something like this. 9x plus 2y equals 15. By the way, notice, what kind of equation is 9x plus 2y minus 15? 5, 4, 3, 2. I think I'm at 80 now. I lost count. 80, we're going to say. Well, this guy is linear. How do you know? Well, it's x to the invisible power of 1, y to the invisible power of 1. This has all exponents of 1 on our variables. If I wanted to test if 1 comma 3 was a solution, what would I do? 5, 4, 3, 2, 81. Very good, invisible person. Well, all I would need to do is substitute. Using my ordered pair notation, I know that x comes first, followed by y. So all I need to do is substitute and check whether my statement is true. So let's take 9 times 1 plus 2 times 3. What do you think? Is it going to be a solution? Only one way to find out. On the left side, let's simplify. 9 times 1, that's 9, plus 2 times 3, that's 6. Is 9 plus 6 equal to 15? Sure is. So this gives me a true statement. It is a solution. But if I take that order, put it down, flip it, and reverse it, and write it as 3, 1, is this still a solution? Do some substitution. You tell me, what do you think? Is it still a solution? Yes or no? Alrighty, well, in my ordered pair notation, This is telling me that 3 is the value of x and 1 is the value of y. If I substitute in here, I just need to figure out, well, does this give me something true? So I have 9 times 3 plus 2 times 1. I want to figure out, is this equal to 15? Well, 9 times 3, that's 27. 27 plus 2 times 1 is 2. That would be 29 is equal to 15. Well, is this a true statement? I don't think so. 29 doesn't seem equal to 15 to me. Can this be a solution? Well, it gives me something that's false rather than true. No, this cannot be a solution. All of this to say, the reason why we call these pairs ordered pairs is because the order that we list our number in is important. The order matters here. Cool. So I cannot willy-nilly write the 1 before the 3 or the 3 before the 1. I have to make sure that I am writing them in alphabetical order corresponding to the variable. Good. Let's take one more. Say that I've got this guy. It's an inequality. Negative 2x plus 3y is greater than or equal to 6. I want you to determine whether or not each of these ordered pairs is in fact a solution of this inequality. Take 2 minutes, 3 minutes, pause the video, do some substitution. Tell me what you think. Go! Alrighty. Well, if I'm taking my 0, negative 4, in this case, that's telling me 0 is the value of x and negative 4 is the value of y. So if I take negative 2 times 0 plus 3 times negative 4, I'm trying to figure out, is this greater than or equal to 6? Well, negative 2 times 0 is 0, so I can ignore this guy functionally. 3 times negative 4 is negative 12. Is negative 12 greater than or equal to 6? Well, I don't think so. Can this be a solution? No, man. How about negative 3, 0? Well, negative 3 is going to take the position of our x value. 0 is going to take the position of our y value using our ordered pair notation. Negative 2 times negative 3, well, that's positive 6. Plus 3 times 0, well, that's just 0. So I have 6 is greater than or equal to 6. Is 6 greater than or equal to 6? Sure is. This is indeed a solution. And finally, 4, 1/3. So 4 is going to take the place of our x. 1/3 is going to take the place of our y. Negative 2 times 4 is negative 8. Plus 3 times 1/3 is 1. Negative 8 plus 1 is negative 7. Is negative 7 greater than or equal to 6? No. So is this a solution? Nor it is not. Fantastic. So now that we've got all of these ordered pairs that can solve our equations or our inequalities in 2 variables, the idea is that we now need somewhere to put all of these solutions. Not only that, but like having a visual representation of what our solutions are is actually going to turn out to be super powerful for us. It gives us a lot of insight into the anatomy of the equations that we're working with, which lets us literally see the relationships that that anatomy creates between the solutions, which leads us to this idea of graphing. Now, we're not going to do some graphing in this video for the sake of time. We'll talk about it more in class tomorrow, but we'll talk about some of the fundamentals. Previously, when I was graphing the solution set of an equation or an inequality, we used a familiar friend from journeys past. What was the tool that I used to graph going before? 5, 4, 3, 2, 82. Well, the tool that I used to graph previously was the number line. But if I want to graph now, there is a slight, in fact, not so slight, issue with the number line. What do you think is the problem? Now that I'm in 2 variable land with using the number line to graph. Go. Take 10 seconds. What do you think? Take a risk, take a chance. Who cares? Well, if I'm in 2 variable territory, the number line isn't going to be appropriate for collecting my solutions, because the issue is that on the number line, I can only talk about 1 variable. So the issue as it stands is that my number line only works for solutions with 1 variable or 1 part. So the way that I'm going to solve this, well, again, another guiding principle in math is if it ain't broke, don't fix it. The number line is still a powerful tool for graphing, but it can only talk about one variable. So instead of using one number line, if I want to talk about solutions with two variables, what if I use two number lines instead? And the way that I'm going to organize these number lines, I'm still going to take my first one, I'll put it horizontally. So I've still got like my value of 0 in the middle, and then I would go negative off to the left, positive off to the right. And then maybe in a kind of weird choice, but in a choice that you've almost definitely seen before. My second number line, I'm not going to put it off to the side to talk about the other values. Instead, I'm going to take it and intersect it with my existing number line, going vertically. So I'm going to take my values of x here and my values of y, put them on two number lines that are going to cross each other. And when I do that, I create what is hopefully this familiar tool for you called the coordinate plane. The coordinate plane has some funky names. You can call it the coordinate plane. You can also call it the xy plane or the xy coordinate plane. By convention, hopefully you'll remember, the values of x typically live on the horizontal one, in other words, going left and right. The values of y typically live on the vertical number line, or the one going up and down. Another word for this, you can call this also the Cartesian plane, derived from the philosopher René Descartes. While he was known primarily as a philosopher, he was also a proficient and prolific mathematician. He was actually the guy who invented this idea, hence why it's named after him. An important, or interesting at least, piece of math history for you. Let's quickly, I can speak words, talk about the basics of this Cartesian plane and how it works. We'll do some graphing on it when we see each other next time. So, this x number line and this y number line, you might remember that they have some fancy names. We call these on the graph the whats. 10 seconds. You don't need 10 seconds. These are the axes. So I have an x-axis. The plural of axis is axes. This one is, of course, the one that goes from left to right, our horizontal one. And we have the y-axis, which is the one that goes up and down. Cool. On our axes, we've got positive and negative numbers, right? As I move to the right on the x-axis, I go up, and to the left, I go down, just like on a normal number line. Logically, if I move up on the y-axis, usually when I go up, I think of things that get bigger. So the logical decision was to make the positive values of y go up, the negative values of y go down. Other things that we want to talk about here. This point, where my two axes intersect, this has a fancy name as well. It is called the origin. It is the place from which our Cartesian plane originates, right? Both of my number lines intersect at this point. Its coordinate, by the way, right, if I think of the point that it corresponds to, it matches with the place where both x and y are 0. So the point 0, 0 is the coordinate, we would say, of the origin, right? A coordinate is just a fancy name for a place on the graph. The last thing that we'll talk about here are what we call these 4 different rectangles or squares that we've created. We call these the quadrants of our graph, and we have 4 quadrants. The way that we talk about our quadrants, the one here on the top right, you might remember if you've learned this before, is called quadrant 1. We usually write our numbers in Roman numeral notation, and we rotate through them counterclockwise. So moving counterclockwise here, this would be our second quadrant in the top left, followed by quadrant 3 in the bottom left, and finally quadrant 4 in the bottom right. Could you imagine if this one was like quadrant 0? It's quadrant 4. So the last thing that I want us to notice, what kinds of ordered pairs or points will live in each quadrant? Look at the numbers here that I've put on our number lines for us. What can you tell me about any ordered pair, for example, that lives in quadrant 1? What can you tell me about the numbers that would need to live inside of that ordered pair? Take 10 seconds, pause the video, talk to a wall, talk to a partner, talk to your friend, talk to yourself. Go! Okay, well, hopefully we've noticed. If I have values of x and values of y in the first quadrant, both of those are positive. So I will always have positive x and y values in the first quadrant. In the second quadrant, though, while the values of y are positive, the values of x as I go to the left become negative. So I have negative x values and positive y values. In quadrant 3, both x and y, you'll notice, are negative. And in quadrant 4, while our values of x switch back to positive because I've moved to the right, the values of y, I'm still in the bottom part of my graph. These are negative. Nice! So this is a place where we can put those ordered pair solutions that we want to find, or more broadly, any collection of ordered pairs. So the last thing that we'll notice here is that each ordered pair corresponds to exactly one point on our coordinate plane. That means that we have 3 interchangeable words to refer to the places on our graph. What are the 3 interchangeable things that we might call these? 5, 4, 3, 2, 83. Well, if I'm talking about my solutions, I know that they are ordered pairs, but I've also interchangeably called this the coordinate plane, so I can also call these coordinates. And last but not least, another word for a coordinate, perhaps a little bit less fancy. I could also just call these the points on my graph. So all 3 of these are interchangeable terms. Congratulations, my friends, you've made it through the end of your first class of Unit 4. When I see you next time, we'll get some practice using the coordinate plane. But for now, take care, be good, and don't miss me too much. Bye.